comments, annoyances, things people want to chat about before we start? Oh, is anybody recording?
Yes, Ben's always on that chat.
Oh man, and the poor guy's ill as well, so he's got a flu thing. So, well, thank you, Ben. Okay, so last week we were talking about nuts and bolts, and I'm going to bring all these little bits of nuts and bolts together to talk about what the simplest kind of radiation that you get out of a plasma is, in my view, and that's in something called the Coronal Approximation, which of course is convenient because half of HAO is concerned with the corona these days. So I'm going to just basically, again, just use the sort of Richard Feynman approach, which is not to be terribly mathematical in terms of his original set of lectures, and just fill you in on some of the things perhaps you didn't learn as a result of the formal mathematics and stuff. So last week we ended up with
the presentation on. It'll be easier for the folks online to see it. It's that little icon, yeah.
Yeah.
Thank you.
If I can find, there we go. Yeah. So again, we looked at, amazingly enough, something that we thought didn't have a lot of business being quite as accurate as it was, and it's not always accurate. It could be off by an order of magnitude with complicated atoms, but we generally found that the way in which the things happen inside atoms tend to be of the same form as in when you have internal degrees of freedom and quantum mechanics. Then you have a threshold energy W or E, and then things tend to scale as E exponent of exponential of E to the minus energy divided by KT, and that's because only the tail end of the electrons influence. And when you do that, you end up with pictures like this for a distribution of electrons which have relaxed quickly inside a plasma to some kind of something close to a Maxwellian, and we end up with being able to say, well, there's X amount of neutral hydrogen in this gas compared with ions. So that's one of the nuts and bolts pictures that we talked about and we managed to compute last week. We talked about various things. This is just for your reference if you want to go back and look at these things. But there are various scaling laws here concerning the way things work out regarding impact of these quick electrons moving around inside the plasma and the way that the atoms respond. And so if you were to look at this table, you could, for instance, get a rough idea of how things scale with charge on the atom and with energy, and you would get some clue, and I'm not going to go into those details at the bottom of exchange and non-exchange, non-electric dipole, all this stuff. This is just in case you ever find yourself going in and having to figure some of this stuff out. You would be able to find out, for example, why a neutral impacting an electron has zero cross-section at threshold. I mean, that in essence, there's nothing other than a very weak polarization interaction potential as opposed to a Coulomb potential, which pulls the electron in, and that gives you a finite cross-section at threshold. And remember, threshold is really important. Okay. So those are all things for you to look at in the future. So let's remember, though, that we've got this reversibility issue in Newton's laws, where if we have an electron coming in or dynamics happening between two classical or even quantum particles, it's time reversible on a small scale, meaning that there has to be a balance of if one is in equilibrium, then the only way you can have a real equilibrium is to balance the things going in and the things going out. So on the left-hand side of this thing, again, I'm giving you a pictorial guide to what's going on here. You have an atom which has this, it is in these square boxes. It has a bunch of electrons around it with a confusing nucleus, the same symbol as the electrons, but nevertheless, you know, this is, and there is no such thing that looks like this, of course. We have just probabilities of distributions of electrons moving rapidly around these things, but these are in quantum states that are stable. Even if you were to excite them, they would live, say, 10 to the minus 8 seconds before spontaneously decaying. 10 to the minus 8 seconds is an extremely long time compared with you know, if you were to look at the classical speed of the motion of these things compared with the radius of the atom, you know, basically you'd have to say in a classical picture, this is going around many times. It's not decaying into the nucleus because we've got quantum mechanics to deal with, but eventually it may drop down. So this is a very long-lived state. So what I'm showing you here in those boxes are atoms that have relaxed and they're in their, say, lowest energy state, and all the electrons are closely bound, happily sitting there. They don't have anywhere to go. And even if one were excited to a higher energy state, because such things are possible in these potentials, that would still be a very, very long-lived state, meaning that from the uncertainty principle, if you have a very long lifetime, then the energy is also very sharp. So that corresponds to, even though they decay what we think is quite quickly in 10 to the minus 8, 10 to the minus 10 seconds or something, that's actually a very, very long time as far as an atom's concerned. And these are basically stationary states with very narrow levels. And so they're going to emit photons when they drop because of conservation of energy, a very narrow range of frequencies. Now that's very handy because knowing the exact frequency of the line center of an atom to within 1 part in 10 to the 7, 1 part in 10 to the 8, that tells you that has a little flag associated with it saying, you know, in my own reference frame, this is my frequency, but if you see me in a different reference frame, and I happen to be moving relative to that frame, or you happen to be moving, then I can tell you how fast I was moving. So I can tell you how fast the atom was moving before I emitted and during the emission of that radiation. So that's a pretty handy thing to have, because when we look at problems we're interested in, like coronal heating, we've got free energy of magnetic field, perhaps sharing its energy in a wave-like motion with at the bottom of a potential where the wave motions of the electromagnetic energy are shared with the kinetic energy of the plasma particles. What we're looking at there is motions associated with the free energy that's used to heat the corona. So in other words, line profiles can tell us about coronal heating. I mean, I'm talking very basic here. I'm not preaching to HAO and the people that understand about all these things, but I'm talking about going right back to sort of quantum mechanics and classical mechanics, relativity, time dilation, all this stuff. And so we end up with a picture here where each atom is giving us a photon, and we're damn lucky to have that to come towards us, and we can measure it, or we can measure a bunch of them coming towards us. And this frequency spectrum of those things reflects the distribution of the speeds of atoms inside that plasma. And that is precisely the kind of thing that we need to know associated with free energy. Sometimes things like reconnection, things like wave motions, viscosity, the dissipation of electric currents. These are all things we want to know about the plasma, ultimately, about things like heating mechanisms and accelerating mechanisms. So this is where the basic photon emission of an atom gets us what we want. Most people in HAO don't give a damn about how it does, and certainly you don't need to worry about it, right? But on a basic level, this is where the information we get is coming from. The other kind of information we can get out of an atom is when it's excited. Remember, we have to get over a potential hump of E over KT. And so we have, if we know what the energy is inside these individual atoms, and we've got a KT on the denominator, we can start telling you something about the mean electron temperature in that plasma by looking at these various things in ratios. So again, I'm just reinforcing what we've already talked about and know, but this is plasma spectroscopy. Another way we can do it, perhaps, is if we know that certain atoms make jumps between these orbitals, but they can't do it before they're interfered with another electron coming along, or some kind of mixing of states by the electric fields due to thermal motions, whatever it is. So now we've got additional ways in which those atoms are going to maybe or maybe not emit a photon. It could be shifted by the electric fields. It could be shifted by magnetic fields. There are all kinds of ways in which the atom itself is going to imprint on us through the radiation emitted as to what's going on inside this plasma. And if we look at what the business of places like NSO and HAO are into these days, it's all about these kind of interactions. And HAO's CMEX mission reflects the idea that we're going to try and use the magnetic influences on these atoms as they're radiating to understand, the emergence of magnetic field at the very base of the corona, as opposed to underneath, down in the photosphere. So, this is all intrinsic and it's all in the background. But anyway, let's look at this this business of reciprocal processes, and let's just look at the top one. So before, we have a state where the atom's got all its electrons around it. It's got 1, 2, 3, 4. It's got a nucleus of 1, 2, 3, 4, 5, 6 electrons. So that's a carbon atom. And now, after the collision, there's some jiggery-pokery going on in between these two boxes at the top there. And after a bunch of rattling and something, it decides to eject an electron. And so what you've got there is one electron coming in and 2 electrons going out. So now we've got an atom of carbon 2, with 1 electron removed. So carbon 1 on the left, that means the first spectrum of carbon has now been collisionally ionized, and we've got 2 electrons going out. Notice that those electrons are gone once and for all. And those 2 electrons are not going to come back because of conservation of momentum and hit that atom. So there's no memory that that atom ever had those particular electrons on it. Okay? That means that in the reciprocal process underneath, those 2 electrons that are coming in, so now we're looking at the second row, we have 2 electrons coming in, and again, there's some jiggery-pokery going on, but the reverse process is such that you've only got 1 electron coming out, and now it's back in the initial state that it was. So that's called recombination. And you got another electron coming out. Now, I won't go into a piece of contention that I got into with Rob Rutten once about rate of transfer and things, but there is an interesting issue there if anybody wants to talk to me about it. If we have photoionization, let's go down to the third row. So that involves a 2-body process and then a 3-body process, right? And that 3-body process, that has to happen at the rate at which look at the second row, the first column. 2 electrons have to come in at the same time, and the problem to that happening is proportional to the speed of each electron and the density of each electron, and it happens so that you have an NE squared dependence in there for the rate of probability at which this is going to happen. And so now we come down, and so that's different from the one above, which is just NE times a cross section for that top one. So what we'll do now is I'm going to show you what the other 2-body processes are, and I'm going to consider the photon as a particle, as I'm entitled to do from time to time, and say that if you have an incoming thing on the third row, you've got a photon coming in, it's got enough energy, again, the H nu over the energy gap between removing one of those electrons, so then you have to rip it out of the potential well with an electric field. And so a photon comes in, and then it knocks an electron off with a certain energy. So that's a 2-body collision with a 2-body outcome. You just exchanged a photon for an electron there. Again, that electron's gone. It's got no memory at all about where it came from or anything. It's part of the pool. The reciprocal process is where an electron comes in, and now it's grabbed by the atom, and then it releases a photon. So if it came in with just the right amount of energy, and was grabbed by the atom so that it would be enough such that the emitted photon, when ionize it again, this might well go through this cycle. But the thing is, those are all two-body processes at the bottom, and those are three-body processes at the top. I'm going to talk shortly about the coronal approximation in which the three-body processes can be completely ignored. Okay? That means that you definitely do not have any kind of thermal equilibrium. It's far from that. And when you have two-body processes, it's very odd to think that in the corona, collisional ionization is completely balanced by radiative recombination. So the top left process is balanced completely by the bottom right process. And those are quite different processes, right? One involves a photon, one involves an electron, but one has got back to the same state of the atom, but you've exchanged an electron for a photon. Okay, hopefully that's extremely clear. So how might we compute? Remember, we computed a cross-section probability for ionization by collisions, but let's look at something slightly different. We'll just look at this principle of detailed balance, because on that bottom thing we showed here, you've got photoionization and recombination. How are we supposed to calculate something to do with recombination? Well, it's relatively straightforward. In fact, I'll do it in the next page. What's going on is we simply say that under thermal equilibrium, the radiative recombination rate has to equal the photoionization rate. Now, how do we know the photoionization rate? Well, we know that the atom is described by the Saha distribution in its balance Saha-Boltzmann. So we know that in equilibrium, these two things must balance, but we also know that the radiation field is a Planck function. So what we have here is a very simple calculation, and here's the distribution function for the balance of populations, Q in ion that's in neutral. So QZ is neutral hydrogen, QZ minus, is ionized hydrogen, QZ minus 1 is hydrogen. And again, we've got the lambda cubed is a length. It happens to be the de Broglie wavelength. And this is Saha's formula for describing in equilibrium what those populations should be. So now all we've actually got to do is to do the following example. To compute the rate at which atoms are grab an electron and emit a photon, we say there's a balance between photonization with the Planck function and then recombination with this distribution of electrons and atoms that we have. And I do that here. I mean, this is a very simple thing. So basically, detailed balance is that top left equation. And we know the stars say this is local thermal equilibrium. And then on the right there, when J is B, we know that the Planck function is described by that distribution. So we have now a formula here for describing, once we replace N1 star over NK star by the Saha equilibrium, and we stuff in the Planck function for the photonization rate, we get these formulae. And if we make some simple assumptions, it turns out that hydrogen has a cubic dependence on the frequency. So as you go to higher and higher frequency, the cross-section drops as 1 over nu cubed in the non-relativistic limit. But we also know that h nu over kT is enormously bigger than 1 because we found that earlier with equilibrium plasmas. I haven't proved it yet. In fact, this is part of the proof, is to calculate these things. But basically what we have here is this very simple way of calculating the reverse process when you know the forward process, okay? And this assumes equilibrium, as I said, the principle of detailed balance. And you end up with something in which, well, you integrate over all the frequencies in the photoionization, and you end up with, when you integrate that out, you end up with, the only thing you can end up with is a function of some thermodynamics. And the thermodynamics is described by distribution function. When you integrate that and if it's in equilibrium, which we assumed here, then you end up with two numbers that can describe that. One is when you integrate over velocity space, you end up with the density. And the density we're concerned with is with the electrons here from the SAH equilibrium. And you also end up with the temperature. So what you end up with is an expression which says that, amazingly enough, very simply, the amount of recombination if I embed a proton inside a plasma, the rate at which recombination occurs is proportional to electron density. More electrons, more probability of it attaching to a proton and making a hydrogen atom. But also it's inversely proportional to the square root of the temperature. That's just the way it turns out. And so what we end up with here, remember the ionization rate was a function of e to the minus delta E over kT. And if I'm saying two body processes balance each other, and this is a two-body process, and we can ignore the three-body collision recombination, then what we've got is a function of E over kT balancing this term here. So what we've got is ionization balancing the recombination. The recombination is a function of temperature and density. Ionization itself is a two-body process, it's proportional to NE. So the NEs cancel out, and we end up with ionization equilibrium being purely, in the coronal limit, a function of temperature, electron temperature, okay? All right. So now there is one interesting, nice little problem here, and that is that if you look at this, hidden under this equation is a nasty business, because if we really formally take an atom on its own and we calculate the partition function at a finite temperature, we have an infinity, because partition function is a sum over all states of the number density in LTE times e to the minus delta E over kT, and we know that solutions to the hydrogen problem have n equals 1, a big jump to n equals 2, 3, 4, 5. That doesn't stop. That goes to infinity. So we have in principle a problem in calculating this that actually disappears because of some of the physics we talked about earlier. The thing that happens is you get bigger and bigger and bigger orbitals, and suddenly the atom is no longer that orbital when you're summing all those high end states, n equals 30, 31, 32, eventually those are going to feel the effect of all the plasma around them. And what that means is that those become essentially free. And so you only have to sum up to a certain finite number to get this partition function under these conditions. This is a crude statement. It's of the ilk of Feynman's lectures. This is how it works. Of course, if you want to do this right, you've got to do the calculations. But it truncates the nature has a way of sometimes being kind to us. It truncates the thing to infinity. And one of the other ways this works is you can think of it like this. Instead of the orbitals, you can think, well, I've got a hydrogen atom. I'm sitting at an n equals 30 level. Even if I'm a long way from the other hydrogen atoms, I mean, maybe I need to go to n equals 100 to find that I'm reaching out to the other hydrogen atoms with my little bits of my wave function. You can nevertheless also say, well, let's just put an electric field on that deep potential. So the potential on the left is the unperturbed hydrogen atom minus Z E squared over R. And let's just put a little static electric field on it and see what happens. Well, it tilts that field according to the right-hand thing. You just add your constant electric field to it, and it looks like this. And so what does that mean? The hydrogen atom is sitting there inside this static electric field, and if it moves up the potential curve to the right, it's trapped more by the electric field. It's holding it in more. But 50% of the time, on average, it's going to move to the left. And you can see that the potential, ionization potential, has been dropped by that static electric field. Now, there is no really strong static electric field in the rest frame of the atoms in a moving plasma, at least at the level of the understanding of MHD and conductivity being so high and what have you. The electrons move around to short each other out. But there is a net thermal noise always at a finite temperature, and that thermal noise generates local electric fields inside the neighborhood of each hydrogen or carbon or iron, whatever it is you're looking at. And so 50% of the time, even with the thermal electric fields, which can be computed very simply using some sort of Debye theory or something like this, where you evaluate what the free energy is in the motion of the particles in this plasma with a temperature T, etc. You can determine what the sort of RMS electric field is, and even if it's very tiny, it lowers the ionization potential and it solves your problem with the partition functions. When you go into the solar interior, this is not so easy. And that's because the densities are so incredibly high there. And people like Mihalis, Deppen have looked at what they call the equation of state for these kind of atoms. This is clearly related to the equation of state because the state is determined by the Saha equilibrium. We're talking about modifications to the ionization potential because of this. All these things turn out to be kind of interesting, and it's a part of the problem of the discrepancy between the models built with helioseismology and those built from scratch, incorporating this kind of physics into the solar interior. Okay, that's just a note that I'm adding here. Okay, now we're going to go back to the idea. So everything's hunky-dory in the corona. We can have a physical reason that we think we can calculate these things, and so there's a Debye radius, etc. You can, a very nice discussion of this in Cooper's thing. Now, so let's turn back to the corona. There is one thing that's slightly more complicated here than in, I don't know why those little red electrons are in there. That's interesting. Okay, never mind. Actually, that is relevant. I don't know how they got there, but
They quantum tunneled.
Huh?
They quantum tunneled.
Yes, yeah, the things have tunneled through into noise and stuff. Get noise on the slides here. So what's going on? Remember, we talk about for hydrogen, we genuinely have one electron, a two-body problem. But then as soon as we impact that with another electron, we got a three-body problem. And let's look not at hydrogen, but well, let's just continue here and see what we're talking about. So let's imagine putting a photon and ionizing hydrogen. The top plot is a plot of the cross-section of hydrogen, where people have, there's good reasons to measure as accurately as you can, photoionization. And this is well known to everybody. At 13.6 eV is the well-known ionization potential of hydrogen. It's called 1 Rydberg of energy. And so there's zero probability of ionizing hydrogen until you suddenly reach this. And then you have this mu cube drop-off with energy, or energy cube drop-off with hydrogen. But now let's look at a slightly more complicated thing. And again, it's a two-body collision, if you like, between a photon and a hydrogen atom. And it has this simple behavior here. And but if we now look at, because that originates because when you have, to calculate this probability, you have to calculate cross-section. And cross-sections are nothing more than the probability of making a state from a bound state of hydrogen. You have your operator, which in this case is going to be called an electric dipole operator, and then you have your final state. And so those are the two wave functions. You square that, and you get yourself a cross section, and that's what's shown there. And here, I think you can see that once you've got enough energy, you've got no degrees of freedom left to do anything very spectacular between this absorbed energy of the photon and the outgoing electron through photoionization. On the other hand, let's now look at a complicated atom. And we looked previously at a beryllium-like ion, where I just pulled a cross-section out of the blue from the web here, and here's one. And so this is, again, a beryllium-like ion, so it's got 4 electrons around it. 1s squared, 2s squared. Now these are highly more excited states. So this is, instead of 1s squared, 2s squared, this is 1s squared, 2p squared. So now we've got, and that's a perfectly valid state. You can, if you can arrange it to be in that state, it's going to sit quite high up because it's got more energy because of the extra angular momentum in the 2p electrons versus the 2s electrons. Now, this is a plot of the cross section from that, whatever that state is. It could be any of them in carbon-3 into the carbon-4 state. So that's 3 times ionized carbon out of 2. And now we see something really very different here. And what's going on? I couldn't find one. I wanted to find one for helium to illustrate this, but I couldn't actually find one very easily yesterday when I was looking. So, but what we notice here is we've got some funny business going on. We've got what looks like a continuum like hydrogen, which is this blue dotted line, but then it's got these little nicks in it, and this is a logarithmic plot. So these are actually quite big jumps in the photon ionization cross-section. Then it goes down again. And these seem to be occurring fairly regularly, perhaps in a fashion reminiscent of the n equals 2, 3, 4, 5, 6 kind of energies of hydrogen, right? So what I'm saying is we now look at the red curves. You come along, and what you'd expect to see if it was just one electron moving around in a potential would be something that's relatively flat like this. But in fact, we see this enormous amount of variation. There's logarithmic changes of a factor of 3 in the log. So it's 10 to the 3 times more opaque at this wavelength than it is down here. Okay, we saw some of these things, I think, just briefly, and these things are called autoionization resonances. I hate to use those words because those kind of words can be rather confusing to somebody who's not familiar with the language here. What this is a manifestation of multiple electrons being moved around at the same time. And it's a question of, so the reason being that it's basically a many body effect. And when you've got hydrogen, it doesn't happen because you only got 2 bodies and a photon's being absorbed. Photon is not the same thing as an electron, and it doesn't feel potential. The only dynamics that's going on is the electron moving around in its potential. And the energy, when it's absorbed, it gives it a kick into a continuum state from a bound state. Here we've got something going on. This looks like n equals 2, n equals 3. If we just look at hydrogen spectrum, we would say, you know, these look like hydrogen lines. In fact, these are the equivalent of the hydrogen lines, but in an atom where another electron has actually been moved to a higher energy state, but at the same time, this is being excited. So you've got 2 electrons excited at the same time. Okay, so this is what we call a double excited state, and you shouldn't really worry about it, and because it's except that these states, because of E over KT, needed to get any kind of ionization at all. That energy barrier is big enough also to rattle around some of these internal electrons within the atoms to make them jump at the same time as another electron jump. Now, you can't make 2 electrons jump with 1 electric field. You've only got one operator going into these things. So, you know, but that's not what's happening here. What's happening is the atom is described by a big wave function consisting of, in this case, 4 electrons, right? 4 electrons, 3 of which are bound, 4 of which are bound in carbon, 3, and then 3 of which are bound, and 1 is free in carbon-4. Right, this is what's happening here. We're ionizing it. H nu plus C2 plus goes to C3 plus an electron with an energy associated with it. Okay, so what's going on here is really that you know, we're not making electrons jump between orbitals in a 1 electron sense. What we're doing is you hit the atom with a certain amount of energy, which causes perhaps one of these electrons to jump. And then in the course of a rearrangement of the internal structure of that atom, another one is jumping as well. And you can imagine holding one steady and then having a Rydberg series built on top of an atom that, instead of being in all the other electrons in the ground state, this one is now excited a bit. And that's what you're seeing here. That's what we're seeing is a bunch of atomic energy levels, but they're being manifested now because as a photonization cross-section, because as the photon energy is increasing, going towards the left, it's starting with a cross-section of, say, 0.5 megabarns here. A megabarn is, I really like that.
Yeah, can you explain exactly what the y-axis is? Like, what is that physically?
That's the cross probability, the cross-section, which when you integrate over all frequencies, atoms, of the photons, that would give you the rate at which the atom would go from carbon-3 into carbon-4. Okay.
So as other energy hits it, that's the odds that it moves.
Yes,
Okay.
that's the same probability as we had before.
Okay.
Okay. And for all these processes, they're all calculated in sort of the same way with different operators and what have you, but it doesn't really matter. So what I'm saying is that, and this was realized quite some time ago by Unsold in German, famous Germanic, I don't know if he's German or not, in the 1950s, that there was a problem because all this nice theory had come around to show that we have a function of temperature only for ionization fractions, but they started observing with people like Leo and in the eclipses and all these other things. We have a prop scan likely again. Then these emission lines, which were not, and then beginning in the 60s in the ultraviolet, they started getting these rocket data. And it turns out that something seemed to be not quite right about the ionization equilibrium of the elements with regard to temperature. So what they did was they had the collision cross sections calculated, and then they did the rates of recombination cross sections, and they had these balances, and I'll show you one in a minute, of ionization equilibria, where iron 10 forms at this temperature, iron 11 forms at this temperature. Now, these turn out to be off against things like radio observations of the Bremsstrahlung emission of the corona. There were systematics that were off. People couldn't quite understand what was going on. And Unsold suggested that, well, we're in a regime where this potential energy barrier to do stuff inside the internal structure of an atom was on the order of I over KT, the ionization. That number's like 10, okay, typically for where these equilibria were producing the state of the atom embedded in this low density coronal plasma. But, this was a puzzle for a while until Unsold sort of suggested there's enough of I over KT here such that it's not just knocking one electron off, but we might sort of have enough energy to knock one electron off, and then a little bit higher energy would excite an internal atom as electron as well. And so if that's the case, then it might end up affecting the things like ionization equilibrium, because these photoionization cross sections, remember the detailed balance, to calculate recombination, I would take these curves and do exactly the handwritten calculation I did, which is just put in the reverse process, put in a Planck function. And now if I've got things that are 3 orders of magnitude here, whereas without those interference, it would look like this, 2 orders of magnitude smaller, this is going to cause one hell of a lot of recombination. I mean, it's a factor of 30 higher than you would expect from a single electron moving around in the internal structure of the atom, okay? So Unsold suggested that, and then there were these people at University College London again, Mike Seaton, and Alan Burgess did his thesis with Seaton, I think in London, and came up with a theory for this, and it basically, again, the simple effects I've talked about are given above, with 1 electron is excited, but now we have 2 electrons being excited here. So I'm just documenting this so you can see it. But basically, if I call out process number 8, you can see that all's going on is I have an ion in state with charge I at level K, and I go to another one after electrons hit me, I plus 1 and J. So that's the collisional ionization. So I just whack the atom with an electron, 2 electrons come off, and I've got this other thing there. That's a single electron excitation, because what's going on there is that the example is shown there is again the 2s squared, the beryllium-like system, and you're ionizing carbon 3 into carbon 4, and you can see it's going from the 2s squared state to a 2s state. So that's described by 2s orbitals and 1s orbital afterwards, and then 2 free electrons coming out. This one, on the other hand, number 11, if you look at that, what we've got there is we've got a 2s electron sitting there in the same way. It's being impacted by an electron, but now what it's done is it's excited the 2p electron and an ns electron. So, for instance, if the electron piles in and is just sort of grabbed by the potential field, and while it's being grabbed, it forms an ns electron. So n might be 10, it might be 5, it might be whatever you want. But in the process of doing that, one of the electrons has also jumped inside the atom. So now you've got a doubly excited state here, this one here, compared with that one. That's a single electroexcitation. This is double. Okay, now this is sitting there in a high energy state because you've got 2 excited electrons around it. Okay. And this thing is a process called, it's just, you can see it's just a many body process. It's called dielectronic capture. Okay. That means that you've gone from an atom, an ion with an atom with, which is, say, carbon 4 and a free electron. It's gone to an atom of carbon 3, but it's now got, instead of a free electron, which is a Coulomb wave, or basically a plane wave almost, and a bound state, you've got 2 bound states in there that are there. So this has been captured. It's localized to be part of the atom itself. So it belongs to carbon 3 now instead of carbon 4. And then, but now let's think about what this means. Oops, sorry. And this will make it clearer, I hope, in the pictorial way. But I just wanted to go through this one for those that are interested in seeing what's going on in terms of orbitals. So then we've ended up with this doubly excited state. Now, this is a pretty unstable condition. So it's going to relax pretty quickly to something here. Okay, so we take that state and we say, well, what happens if it just goes 2p to 2s and just chucks the electron out? Well, then we got back to where we started here, right? So it's a reverse process. And it's called autoionization. It just means you've got a doubly excited state from an electron that's come in and whacked it, and now you've got a singly excited state and the electrons carried on. Could be the electrons have swapped, for instance. So it's not necessarily the same electron, not that it matters because they're all the same anyway. Okay, but then something else very interesting can happen, and that is that we're in this 2s2p 2p-ns state, but now what happens is instead of it going to just throw the electron back out as a reverse process, this may well decay down to a 2s electron. See that? We've gone from 2p to 2s. And also we've got something like an n electron as an in its own state. That should probably read ns, that one there. But what's going on is that it's relaxed to a lower energy state. Remember, this is 2p, which is high up. Now that internal electron has dropped and it's left itself in this other state, but it's emitted that photon. So what's going on? It just means that atom has relaxed, but it hasn't gone all the way back to throw the electron out anymore. Instead, it's emitted a photon, and then it's gone back to a state where it's got an NP electron around it. And if that one relaxes somehow down to 2s eventually, or 3p or something, then it emits yet another photon. And so what you've done there is, instead of capturing an electron, going into double excited state and then throwing out again, capture an electron, going double excited state, oops, it slips down in a different way, and then it's got 2 bound electrons still because it's got rid of some energy, H nu primed, and now that decays again to produce another photon, H nu double prime. So what we've done here, we've started from an impact of an electron on an atom, we've double excited it, and we've ended up with a recombination that's not described by the kind of recombination we just talked about, radiative recombination. And that occurs through that's what's going on right here. Okay, that contribution to that recombination is in the peaks of these things, which don't exist if you don't have multiple electrons. So it all kind of makes sense.
Bill, can you go back to that slide? The energy of the incoming photon is decreasing as you move to the right in this diagram.
Yeah. Yeah, so so there's a threshold around 440 or so, at which you need to start ionizing this thing. And then, but the thing is, these doubly excited states start to kick in right then and there, which don't exist, for instance, if you reverse the axis on the top plot. There's no such, there just aren't any resonances at all there.
Okay, thank you.
So the bottom line of all this is that the internal dynamics is not just single electrons jumping out in and out of a atom. They can include double, triple, whatever you want. I mean, if you hit this thing with an X-ray, you knock a 1s electron out, the whole thing piles down, right? You've got electrons, and so that's potentially a many electron relaxation, and that's all that's kind of going on here. And the significant physical point is that because I over KT is almost enough to excite these doubly excited electrons in many cases, then you better include those doubly excited electrons. That's the basic point from about 1950s. Okay.
How about triple excitation?
Yeah, that's just, you keep having to get these compounded E over KT barriers you've got to get over.
Mm-hmm.
And at some point, you know, with the energy is increasing as 1 minus 1 over n squared kind of thing in the energy of the bound states, those kind of tail off.
Okay.
I don't know of any that are believed to be important in astrophysics, at least. So let's make this a little bit more pictorial. In fact, that scary business is not that scary at all. Instead, we have a picture like this. In comes the electron on the left-hand side, whacks into this thing. It can excite this electron. The star says, "Oh, you know, I'm in a not in the ground state anymore. I've taken some energy out of that incoming electron, but there's another electron leaving with less energy." And then basically this can decay and emit a photon. So that's called collisional excitation. The thing about dielectronic recombination is we have this incoming electron again on the left-hand side. And again, it's a two-body process, which is why it's important. And then, but instead of exciting just one electron, two of these electrons get excited, which is a perfectly valid outcome. These are, after all, the idea of an individual electron is just our projection onto a certain kind of wave function as to what might happen next. So the complete wave function of the atom is a description of the nucleus plus all these electrons around it. And we're just saying to ourselves, well, we can most easily understand this by identifying each electron with its own principal and angular momentum quantum numbers. And we're just saying that the total wave function now looks like most of the electrons aren't doing anything, but there are two of them now that have different quantum numbers. Now, this is the dielectronic capture. You can see I've got two electrons excited, but they're still localized. There's no photon electron going out. Now we go to right again, and we say, what happens if one of these electrons drops down to the ground state? So one of those stars has disappeared. We've still got an excited state. An electron goes off, and now we've got a star in that state with an electron going off. So we've got electron coming in, electron going off, but we've excited the atom. This is called that process of dielectronic capture followed by autoionization. You can think of it like that, or you can think of it as being just collisional excitation. Because after all, what's happened is we've got an electron coming in, we've got an electron coming out, and the final result is we've got an excited atom. That excited atom is going to radiate a lot of photons into space as a coronal line, for instance. Okay, so this is really not much more, this is just a little bit more complicated process than the effect of collisional excitation. And now I think what you can see is that if we do end up with an electron coming in and these two electron states start to get excited, those will occur both in photoionization, both in collision, any kind of collision. So you should expect these resonances in all kinds of processes associated with plasmas impacting these ions. Now let's take the lowest possible arrow there and go down to the final state here. So what happens there is we have the dielectronic recapture. We've got the electrons being grabbed, two excited states. One of those then radiates a photon, but we're still stuck with one of them in an excited state. And that when that excited state drops down, that can't ionize, doesn't have enough energy anymore. The photon's taken the extra energy needed to ionize it. And so what's going to happen next is that thing is going to sit there and radiate again. So that's again a collisional excitation. But what we call that is, because there's no outgoing electron anymore, we call that dielectronic recombination. Okay. This is another way to look at it. I'm not going to go into this, but again, it's in the article by Cooper, which I like so much. If you wanted to read about this, this is the sort of beginning of this process. The reference is right there. Here are the resonances which occur as a result of these double excitations. If you have a fully permitted transition with one electron jump, these resonances aren't terribly important. And so that's why something like the Van Regemorter formula works. It's because if you use something like the Bourne approximation, you end up with a description for the interaction between the incoming electron and the atom. You end up with an oscillator strength determining what the collision rates are. And that comes from these very long-range Coulomb interactions. The resonances aren't terribly important in those things. On the other hand, if we have something where we have to exchange an electron, because now we're going from a spin up to a spin anti-parallel to a spin parallel collision, that probability includes all these resonances. And look at those resonances where they are. They're right at the threshold. That's really bad news if you want to have accurate cross sections. So what it means is that for these kind of transitions that in which you don't have this long-range interaction, you better take care of these resonances. Furthermore, look, that's dropping with energy, that cross section, as opposed to the permitted transitions, which have a sort of logarithmic dependence on energy. And so what you end up with is certain kinds of transitions. I'm just warning you, I'm not going to go into more explanation of this, but certain kinds of transitions have a different behavior. I mean, in the worst case, you can look at things like this, in which it just looks like all hell has broken loose, right? And these are right at the energies for, again, it's a carbon-3 atom. I keep picking that one because it's familiar and we've looked at it. So imagine integrating that. This is a partial collision strength. So this is when you expand your interaction potential, you end up with various angular momentum states which add up, and you've got to integrate to infinity. This is just one of those. I mean, the good thing is that you sort of average some of this stuff out. So if you make mistakes in where they are in energy, maybe there's some hope that if your ab initio calculations can work. So this is pretty tricky, but these things are real and they are absolutely observed. And the experiment is top left, two sets of calculations for an ion of ion 19 to ion 18, dielectronic recombination resonances. I mean, the agreement is just really impressive. And this is possible now due to the fact that you have these little magnetic traps that you can hold ions in for a long time, and you can bombard them with electrons of a monochromatic energy quite easily. And so you can measure the probability of an outcome, and that's what this rate coefficient is. And I want to show you what the net result of this is. Okay, so what are we looking at here? Forget all the photoionized zone and all that stuff. Just simply look at this solid curve without any error bars on it, on the left or on the right. that is T to the minus a half or T to the minus 0.7. That is radiative recombination, one electron process. Okay. Now let's look at what actually happens when you measure it. And when you measure it, you find that around 20 electron volts for this particular iron 19 thing, things start to depart, and the rate coefficient starts to go up. So the probability of making a recombination is now, and by the time you get to say 10 to the 3 eV, you're at least an order of magnitude off in estimating what the recombination rates are. And that's because these are doubly excited states here in this region. And this is just the background radiative recombination like hydrogen. So that the reason this is so important is these bumps, this is iron 19, so that's a flare-like situation, the way that would show up. These bumps occur all over the place in the sun's corona and transition region and what have you. I'm going to step through here. Don't worry. Let's not worry about that. But I just want to show you what this thing looks like. Here we go. So there's the radiative and dielectronic components. This is for helium. So this again is a very small number of electrons here. H plus an electron. And if you just include the radiative component and don't allow these double excitations, you're off by much more than an order of magnitude. And what's really interesting here is that this energy where this is off is at something like 2 to 3 10 to the 5 Kelvin. It's even off at a few 10 to the 4 Kelvin. So this is in fact the dominant component of recombination for helium. And if you don't include it, you're going to be off. You're really going to be off in the ionization equilibrium. So that was sorted out about 60 years ago. And I want to point out, this is what if you're not familiar with this is just an old plot, but and it's a little messy, but let's just focus, say, on a few of these curves. And so what this is when we do a calculation, we take a density and a temperature, and we just crank up the temperature at the same density. And as the temperature goes up, we start to ionize neon 1. So the population of neon 1 is given by that first curve, which starts to peel off around a few 10 to the 4 Kelvin, and it drops like a rock. And it ends up down at the bottom of 10 to the 5 Kelvin with a population of 10 to the minus 7. So this is just the effect of the potential barriers for ionization. So then, if we look down here where the heat neon 2 is, we see e to the minus delta E over KT is very, very small. Neon is very small number. Neon is a noble gas, so it's very hard to ionize. But as soon as you start increasing the temperature up here, you start to create neon 2, and that drops off like this. Then we have doubly ionized neon, 4 times ionized neon, 5 times. So this is just crawling up the steps in the potential energy to create more and more of these ions. But look at these things out here. This is dielectronic recombination, this tail. And I can tell that because it's up against something here, which turns out to be neon 9, which is neon with 8 electrons removed. That's a helium-like neon. I've got to do a hell of a lot of it, put a hell of a lot of energy in to really rip those electrons out from an 8-time charged neon helium-like ion. And so what that means is very robust. It's got a very deep ionization potential. So if you look at these plots, these always correspond, these big broad things always correspond to a noble gas, helium, neon, whatever it is. If I'd chosen argon, there would have been another one to the left, because it's just that we when you've got 10 ions, the plots can get rather confused. And so what I'm showing you here is, if we showed you this for ion, these would all be to cock without this. This is a dielectronic combination, because what's going on is there are electron impacts with a closed shell and very little dielectronic combination to those levels. But underneath them, the things like the lithium-like ions are very much affected by this. And it's known that lithium, and so on the left-hand side of the periodic table, those are easy to ionize. On the right-hand side of the periodic table, those are hard. And remember, we're just removing electrons off to move neon towards a helium-like ion. So we can look at the periodic table, and we can equally talk about helium and neon 9 as the same kind of physics, or argon 19 or whatever it is. So that what's going on here is the patterns here are very reproducible, and I can immediately point to you and show you there's 2 electron excitations going on here, or there's a single shell excitation going on here. And the deal was that I brought up, oh, we're 2 minutes over, I'm sorry, folks. The deal that I talked about earlier about the corona and its and the discrepancies in temperature, when you increase recombination, you move all these plots towards the left. And that is the thing that needed to happen to produce something in agreement between these various ways of measuring the temperature with ionization equilibrium and with radio. There are some other methods as well that were used. And so all in all, things became very clear only in the 60s. The language is appalling. I mean, who wants to use autoionization and dielectronic recombination? Then we have density-dependent dielectronic recombination. Then we have, I mean, it just goes on and on and on. But the basic physics of it is pretty straightforward. And all you need to know is that apparently the corona, and this gets back to Tom's question very early on, you know, apparently there is enough averaging or something that the concept of a temperature as being meaningful and determining the state of these atoms, namely the assumption that the electron distribution function appears to be, you know, is compatible with a thermal distribution function. That is the basis on which I'm saying that these coronal ions are compatible with thermal distribution functions, in the sense that all the thermal physics that we've put in and recognize these processes all seem to have come together some 50, 60 years ago. And people nowadays are looking to push to find departures from this stuff. And sure, I think in various cases you can find them. But really, what's surprising to me, and maybe it's not surprising, but let me put it like this. Why does the temperature, electron temperature, work so well to describe the distribution of material in the corona and its radiation? I mean, it seems to me as if there's every reason to believe that tails and distributions should not produce this thing. But on the other hand, look how broad these things are. These are a factor of 2 in temperature broad, these contribution functions. So each ion, people write down, it forms at 10 to the 6.16 Kelvin. Yeah, plus or minus 0.2. I mean, why would you give all those significant figures? I mean, you know, it's so what I'm saying is, as best we can tell, the remote sensing allows us to say that it's compatible with thermal conditions, but the alternatives, we don't have a good enough forward model to make an assessment of how that would depart from it as yet. But I'll leave it at that because we're running late. That was probably the messiest talk I've given in this series, but I wanted to show you that you could deal with these 2 body processes and then these internal degrees of freedom. That is what coronal physics is really about. The 3 body stuff is more or less irrelevant there. And then later, you know, maybe after I come back from Switzerland, we can start again or something. There'll certainly be one next week. Later we can talk about the LTE part and the non-LTE parts. But the coronal, simple though it is with 2 body processes, it's that there are traps that you fall into, and you better take care of those. But I currently believe that most of that stuff, for instance, observed with decist in iron 13, iron 10, iron 11, all this stuff, that stuff is probably well understood in terms of its thermal physics. Leave it at that. Sorry I ran over, everybody. I wasn't paying attention.
Thank you.
Thanks, Phil.